Now we're going to discuss why it's important to use regularization when fitting logistic regression models. And this relates to a property of our data that's called linear separability. So, as we mentioned in the last video, underneath the hood, sklearn automatically applies regularization. The default is actually L2 regularization, but it has the ability for you to change that to be L1 if you choose, or to set it to none. But in general, I'm going to strongly recommend that you include regularization when fitting your regression models. And the reason is as follows. So first I want to define what's called a linearly separable data set. And there's some words here about hyperplanes and things like this that are a bit tricky. So I'm just going to show it to you visually first. If you just have one input feature, like we had in our example with mean radius, that data set will be considered separable if there is some x cutoff, so some radius cutoff, for example, in this picture right here, such that for any value to the left of that, all of the data points are in the same class. Any value to the right, all the data points are in the other class. So this is considered separable because I have this cutoff point at which all the data points to the left are in one and all the data points to the right are in another. This data set's not separable. There's not a way for me to pick a cutoff point. I mean, I could try this, but then you see I have mixed classes to the left here. There's not a way to do it such that, like, even if I go all the way out here, yeah, the data to the left is here, but the data to the right is still mixed. So that's called not separable. And this idea can extend to higher dimensions. So that's this whole idea of a, quote, hyperplane. When we go up to 2 dimensions for our input features, so in this case, I'm modeling different data. I'm modeling some information about flowers here using their petal length and their petal width. But we're able to see I have nicely what's called separable data here because I can come up with a line such that to the one side of the line, all of the data points are in one class, and to the other side, all of them are the other class. This one's not separable. There's not a way for me to draw a line that separates them. And by that, I mean linearly separable, right? And this is important because the whole idea behind our logistic regression model is that we're actually coming up with a cutoff like this, a decision cutoff point. Like in our previous example, we were coming up with what's the cutoff for which to the left we would classify the tumor as benign and to the right would be malignant in our previous example. If we were to add in more predictions, we'd end up having something like this. If we added, say, another feature about the tumors, and our model would be working on getting this line for which we would classify our data into 2 different groups. So that's a great thing. I mean, that's a nice thing about logistic regression models is they really are coming up with this. It's called a decision boundary, and that decision boundary is a line for the logistic regression models. If your data is not separable, there's not a way to come up with a line that does this perfectly. Okay, why is this a problem? So the problem comes in the fact that ideally, you would think having separable data is your best case, right? Because we're trying to classify data, and if it naturally can be classified and separated by a line, I mean, this is a win-win. You would think so, but it turns out that data like this, that's separable, throws some real curveballs to our cross-entropy loss function that we use for logistic regression. And let me show you why mathematically. We're going to go back to just a single predictor and a very simple toy model. In fact, for this model, I'm only going to use, I'm not even going to include an intercept term. So we'll just have one theta we're trying to fit. And I would like to know, like, what's the best theta if this was the only data that I had. So I want you to take a minute based on what you know about our cross-entropy loss function and what we're trying to do. Can you figure out of these 4 choices, what would be the optimal weight theta? So which theta here would actually minimize our loss? Okay, as a hint, remember what we're trying to do is optimal theta is trying to push the probabilities in the direction of the true class. So ideally, if I input -1 up here for x, which would give me this for my actual probability function, I would ideally want a theta that would make this output be 1. And similarly, if I input 1, I would ideally want a theta, same theta, right, that is going to push this to be a 0. So that's really what I'm trying to do, is figure out which theta will get this output closest to 1 and this output closest to 0. And if you recall back from your calculus days, in order to get this output to be 1, I basically need this whole term to be 0. And the only way I can get e to a power to be 0 is as that power goes to -infinity. And similarly, if this is going to -infinity, well, then I now have e to a positive blowing up. My whole denominator is getting huge, and this whole thing will go to 0. Okay, so this actually means that to find the best weight, if we're trying to minimize our cross-entropy loss, our machinery is going to say, oh, we should just let theta keep getting more and more negative in this scenario, right? In this particular toy example. And actually, if you go plot this, so this is your average, your mean cross-entropy function. It doesn't look like it here, but this is actually slightly going downward, 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 downward. So your optimizer is trying to find the lowest point here, and it's just going to keep going and going and going and going until you stop it, or until we impose some type of restriction. So that's really what regularization is going to do, is when you have these simple cases where ideally this should be our best case scenario, there's a great, we could pick any one of these cutoffs for our decision boundary. I could pick that one or that one or that one or that one. Any of those would be great for my decision boundary. But in these cases, this whole machinery and the math behind it really struggles to find the best fit. Ideally, if you did let theta go to -infinity, what this function will approach, it's actually going to get closer and closer to this step function. It just looks like this. That would be basically the calculus ideal solution for this data set. And that's what we can see here. Okay, but the problem, so again, we have a problem because we can't let theta numerically in our actual algorithm. We can't just let theta keep getting more and more negative. We'd have to stop it somewhere. And even if we imposed a stopping point, the ideal stopping point is somewhere where I get this perfect step function. So I could override this form of the function and say, no, in the cases where it's starting to go to -infinity, let's just replace it with the step function. Again, the problem with that, though, is now notice what it's going to predict. So think of me training my data here on these two data sets. And now all of a sudden I have this data that I want to use now to predict. I want to use my model to predict this new input. Okay, so what will it do in this case? Well, it's going to do what's called, or have a problem with what's called overconfidence. Because suppose my new point has an input of 0.51. Okay, the model is going to classify. It's going to say, no, an input of 0.5 should actually get pushed into the 0 class. So it's going to predict 0. But then look what's going to happen to my loss. I'm going to end up, here's my loss function, I will get a log of 0. My loss will be infinite. And this is also a problem. I do not want to have infinite weights. I do not want to have infinite loss. So I need a way to basically help my model in these simple cases where I have linearly separable data, help it not shoot off to infinity. And that's really what happens with regularization. So to avoid large weights, we use regularization. You will standardize the features first. And as I pointed out, the built-in one is L2, so that's why this is squared. But you're welcome to use, let's see, this is alpha here. You're welcome to play around with it and look at L1. just showing you visually how this works now, instead of having this be the function that we're trying to minimize and we just keep going off to negative infinity, when we add regularization, we're going to end up with a minimum here, that's like kind of right around there, which is great because it's kind of balancing the fact that we don't need a perfect step function. I don't need this as my output. I might, stop with something a little less steep, and that's going to be good enough. And that's really what this is going to give me here. So in terms of what you need to do in sklearn to add this regularization, it has the penalty type, like I said, the default L2. And then if you want to pick the amount of regularization, the default here is 1, and it's a hyperparameter called C, which is basically equivalent to that value Q that we did in our regularization video. But all you really need to know is the inverse of this alpha. Okay, so if you would like minimal regularization, you don't want a lot of regularization, you can set C to be big, right? Because then your alpha ends up being pretty small, and you're not really adding any regularization, and vice versa. So this is an overview of why we strongly recommend you're using regularization whenever you're fitting logistic regression models, so that you can help the model not kind of overthink and end up in a crazy solution when you have linearly separable data.